All right, welcome to AP Chemistry Podcast 16.8. What we're going to do now is we're going to tie in the concepts of free energy, delta G, with the idea of equilibrium and the value we got for K. And if you think about what G told us or tells us, it tells us if a reaction is going to be spontaneous, if it's going to keep going. So if you recall, when the value for G is negative, that means that reaction is still favorable and it's going and it's spontaneous. The question is, when will it stop? Well, it'll stop when you've either reached equilibrium or when you've used up all the reactants, that kind of thing. But for us, in this chapter that we're doing, we're really dealing with the situation where we are at equilibrium. And so at equilibrium, what's going on? Well, that point is the lowest possible free energy. And free energy, again, is that energy that's available to do work. And so if we look at the value for delta G at equilibrium, it's got a value of 0. Remember, if it's negative, the reaction is spontaneous. If it's positive, the reaction is not spontaneous. So at that point where the value for G is 0, Q would equal K. In other words, we're not making any more products, we're not making any more reactants. We are at that state of equilibrium. So what we can do is we kind of can tie those in with this nice little equation right here that tells us that the change in the standard free energy is based on the gas constant, and that's the 8.314, times the temperature times the natural log of K. And so we're going to calculate that out, and because in AP you're often asked to either find G based on the equilibrium constant, or you're sometimes asked to find the K based on the G value. So let's just take a moment to look at this chart. So as I already mentioned, when the value for G is 0, you could say that K equals 1, but essentially that's the equilibrium. Now when the value for G is less than 0, the K is greater than 1. And what does that mean? If it's less than 0, we know that G has a negative value, right? And we know that that's a spontaneous reaction, and therefore it'll go. So how would that relate to K? Well, that means that K is positive, and so we are going to make products as product favored. What about a situation where we have G is greater than 0? In other words, G is positive. We know that's not a favorable thing, that's not a spontaneous reaction, and therefore the K value for that reaction would be less than 1, and so that reaction would be more reactant favored. Well, let's look at a reaction which is very similar to the type you're going to see. And here you have a corrosion of iron, which is good old rusting. And here are some values. There's some delta H values and some delta S values. And what we're going to do is figure out exactly what would the equilibrium constant be. So we want to go ahead and find this value right here. And since you guys are all really good at math, plugging in the numbers is not going to be an issue. But look what they gave us. They gave us the heat of formation and the enthalpy, the entropy values, and so we've got to calculate that out. So again, just as a quick reminder, remember, delta H equals the sum of the products minus the sum of the reactants. Remember that stuff? So rather than me calculate that out, because you guys have done that many times, I'm just going to write the values that I got, and when I work that out for delta H, I get a value of 1.652 times 10 to the 6th joules. Now, I did get it in kilojoules, right? But I went ahead and converted it to joules. And then when I work out the delta S at the standard conditions, I get a value of a negative 543 joules per Kelvin. Okay. Oh, and I should mention also this value over here is negative at the same time. So what does that bring me to? Well, that brings me to the value, or to the good old equation. Gosh, I hate this stuff, right? Remember this? H minus T delta S. These are all standard conditions, by the way. Okay. And so when I plug in the values, and again, I definitely check this with your calculator, make sure you're getting the same values that I do. I get a value for delta G being negative 1.490 times 10 to the 6th joules. Okay, quite a bit of free energy. So now I've got this value that's sitting right here. Oops, I've went ahead and got this value. So let's plug it into this equation. Let me give myself a little bit of room here. All right, so I'm just going to plug in the numbers. Actually, you guys know me. I like to rearrange things. So I'm just going to go the natural log. All right, sorry about the phone. Anyways, the natural log of k equals delta G naught over negative RT. All right, and so now when I go ahead and plug the numbers that I get, which is the negative 1.490 times 10 to the 6 joules, and I put that over negative 8.314 joule Kelvin mole times a negative or times 298K. When I work that out and put that into my calculator, I get 601. And again, that equals the natural log of k. So remember, what I've got to do is I've got to basically take e to the 601, which is some ridiculous number. I don't even know if your calculator would hold that. So the important thing in here is that the equilibrium constant for this reaction is super, super huge, which tells us that this reaction is definitely going to go forward. And so thermodynamically, you can see that the idea of rusting is very, very favored, and which is why we have a lot of rusting in our world. So there you go, some simple stuff, and we'll go over a few problems. And again, like any time, if you have questions, we'll talk about it in class. See you next time.